Welcome to this episode where I shall be looking at the revision of the Physical Sciences Paper 1, okay, for September for the preparatory examinations, okay? So in Paper 1, there are a few topics, or the structure of the paper that we can look at is number 1. We always expect to have some 10 MCQs, okay, multiple choice questions, and they normally account for 2 times 10, which is like 20 marks. And these MCQs will cover all the topics of paper 1. Then number 2, we have the motion, okay, or laws of motion. That's another topic. And then number 3, besides this motion, or we can just break down the motion and say it's normally the vertical projectile motion, okay, where the laws of motion need to be used. And one thing that we need to put into consideration is basically the directions that we normally use. Okay, so the laws of motion normally take between, I think, 2 questions. And then from there, we can have our momentum, in as much as momentum is also still motion, but it's fine. So that's momentum together with the cousin called impulse, okay? And then after that, we can have our work energy and power. And then from the work energy and power, we need to know at least that theorem, okay? What is it equal to, and how do we transform it from words into its application? And then next, we have what we call the Doppler effect. Okay, usually this is 1 question, just like the work energy and power. And then from Doppler effect, we have what we call the electrostatics. Okay, electrostatics. We need to remember the Coulomb's law and the formula, okay, of calculating the force and all of that. So it's also 1 question. Then besides electrostatics, we have what we call electricity, which is basically electrical circuits. And then from electricity, we have the motors and generators, electrodynamics, normally call them motors and generators. And then lastly, we can have our photoelectric effect. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have basically 9 aspects, so areas that we shall be focusing on. Okay, so I'll try to follow the order of the question paper. Okay, but in most cases, when I'm advising learners, if you're writing any paper, start with any question that you are comfortable with so that you can maximize the amount of time at your disposal. Okay, question number 1, which is the multiple choice questions. They're telling us that various options are provided as possible answers. The following questions must choose the answer and write only the letter A to D next to the question number. Okay, so question 1.1. They are telling us that the impulse delivered by a net force, okay, impulse delivered by a net force that is acting on an object is equal to impulse delivered. So we know that impulse is also the change in momentum. Okay, change in momentum is also the same as impulse. The change in P is the same as the impulse. But now we're talking about the net force. So impulse delivered by net force is equal to the change in momentum. So I'm going to go with option C, because option A talks about the initial momentum. Nope. Final momentum, rate of change of momentum. Rate of change of momentum is the force itself. But now they're talking about the impulse. So change in momentum would be the best option for that question. Then 1.2, the graph below represents the relationship between the net force as well as the displacement it undergoes. And then the force and displacement are in the same direction. So if we have F net is equal to delta X and something that we don't know, what are they looking for here? Because that's not mass and acceleration. Okay, which one of the following statements can be deduced from the graph? They're telling us that the area between the graph and the displacement axis represent the net work done. I think that makes sense. But does it make sense? Net work done, if you look at the area that is under here, because we know that for us to get the area here, it's going to be force multiplied by the displacement, which is correct. Okay, which is correct. Work done. Let's see. The area between the graph and displacement represents the power. No, with power, there has to be time. We don't have any delta t, so we can't use this. And then the gradient of the graph represents the change in kinetic energy. Change in EK is equal to W net, the net work. And here we're just looking at the net force. Okay, so this is out also. Then the gradient represents the work done. When you talk about the gradient, so it's like F net over the displacement, which is like the work done by the force. Is that true? Nope, 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 nope. That is not true. Because we know that work done. Okay, remember we said work done is this force times the displacement. Now, if you have the force over the displacement, then that is like the reciprocal of work. So the best option for me would be option A. Then 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The VT graph describes the motion of the ball from the time dropped. Ignore the effects. Okay, so from here, velocity 0, which means it was just dropped. It attains the velocity by the ground. Okay, then bounces off and reaches its maximum at D. And then goes back again for the bounce. And then reaches also a 0 or the maximum at that point. So in the relation to the velocity time graph for the bouncing ball, which statement is correct? Okay, we need a statement that is correct. They're telling us that down is taken as a positive direction and the ball is at its highest position at point C. Nope. So this C just cancels the whole scenario. This is out. Remember, maximum position is basically D and that other point, okay? Or even point B. I wouldn't really call that. Okay, let's see. But I'll go for this one to be the maximum position. Okay, then option B, down is taken to be positive. This is also wrong, okay? And the ball is at the highest point at D. So the last part is correct, but then the first part is wrong. Then C, down is taken as negative, okay, which is correct. And the ball is at its highest at C, which is wrong. This last part is wrong. And then down is negative, the highest point is D. So D is the best option. And then 1.4, they're telling us that an ambulance approaches this person as he is standing beside the road. As the ambulance drives away from him, the pitch and the wavelength of the siren that he hears will undergo the following changes. Okay, so we know that the pitch refers to how loud or how low the sound note is. And if the ambulance is moving away, the pitch is going to be lower. Okay, the sound notes are going to sound low. And what is wavelength? Wavelength refers to the distance. The distance between will just increase. So option D is the best because I'm seeing lower and greater. This is lower and shorter. So D is the best option then. Then 1.5, an absorption spectrum of an element forms because of atoms in the element that are or that will absorb, because this is an absorption spectrum. So there is no an absorption spectrum emits. No. So A is out, B is out. Let's look at C and D. So absorbs light, photons, and atoms, electrons, making a transition from high to a low. Absorbs light, photons, and atoms, electrons, making a transition from low to a high. So when it absorbs the light, it gains energy. And there's no way you can start from being a hero to a zero when it comes to this sort of absorption spectrum. You always have to start from a zero and then become a hero. So option D becomes the best. Okay, start from zero, you go up. All right, then 1.6, two objects with the same mass, with a certain distance d between them, exert a force on each other. Okay, if the mass of one object is doubled and the distance stays the same, the force between the two would also be doubled, because we know from Newton's law of universal gravitation, Gm1 m2 over r squared. If you change this by 2, which means the entire force is going to increase by 2 also. So option C would be the best. If ever it was the distance that was doubled, then the force would be now a quarter. Okay, if both masses were increased by 2, they were doubled, then the force will be 4F. All right, then 1.7 diagram below shows a point P at a distance R from a charged sphere Q. And then they are telling us that the electric field strength at P is directly proportional to R and to the right. So let's start by finding out what's the formula for electric field strength. So we know that it is K. Is that really correct? Because it's a KQ over R squared, yeah? Something like that. But now when you look at the electric field strength and the whatever the distance, they are inversely proportional. Let me just confirm with the formula. I don't want to mislead people. Let's confirm it. We said electrostatics. Okay, so it's KQ over R squared. Thank you. All right, so if that is the case, so option A is out. It's not directly proportional. Option B is out. It's not directly proportional to the square of the distance. So these two are out. Okay. Then C and D inversely proportional to the square of R. That's okay. Inversely proportional to the square of R. And then they're telling us it's to the right. And then this one is giving us to the left. So we know that if P, we normally take P to be a positive charge, okay? And if it's a positive charge, what's going to happen here? It's going to be attraction, okay? So the electric field is saying it's going to be attraction, this one, this side, this one, that side, okay? At P. So when you're focusing on P, the force, this force will work on P in that sort of direction. Does it make sense? And then this one will work in that sort of direction. So I want to believe that P is going to have inversely proportional to the square of R, and it's going to be on the left of P. Okay, so that is 1.7. Then 1.8, which of the following statements about an AC generator is true? They're telling us that the minimum potential difference is not 0 volts. This is wrong. The EMF produced decreases at the number of windings. This is wrong. the EMF must increase. The maximum value of the AC can be increased by increasing the period of rotation. Nope, you can't. Then the maximum value of the AC produced can be increased by increasing the speed. That's correct. So option D is the only correct option there. Then 1.9, a battery with internal resistance connected to a fixed resistor R. The voltmeter is connected across the battery. As we can see in diagram A, the battery is replaced with one with the same EMF, but with a larger internal resistance. Okay, as in B. So this is 0.4, this is 0.2, okay, as we can see. Then they're asking us that how would the voltmeter reading and the current through the fixed resistor change compared to A when the switch is closed. So when you look at this in diagram B, so our focus is mainly on diagram. Is it B or A? Because they're telling us that the battery, because our focus was A, the battery is replaced by one with the same EMF, but with a larger internal resistance as shown in B. 1, 2, so the same EMF, but it's just the internal resistance that is greater. How is this going to affect the reading of that? Now, one thing we need to know is that the current, okay, is it going to increase or decrease? So if resistance, whether it's the external or the internal, if any of them increases, and we see that it is just one resistor, so everything is in series, definitely the current must decrease. Okay, so I'm looking at option A and then option C. There's no way current will stay the same if the resistance values are changed. Then with the voltmeter, we know that voltage is directly proportional to the current. So if the current reduces, even the voltage must reduce. So option A becomes the best option there. Then 1.10. 3 light bulbs are connected in series. Okay, the bulbs are marked 12V, 3 watts. The effective resistance produced by a single bulb in the circuit is, they are connected in series. Perfect. They're asking us to get the resistance. We have the power, which is 3 watts. We have the voltage, which is 12. They're asking for R. So we can use a power formula. We know that P is IV, but our interest is resistance. Okay. So if our interest is resistance, which means we're going to have to say that P is V squared over R. Let's just do this, which is a V squared over P. Our voltage is 12 times 12 divided by 3. Okay, so by 3 is a 1, by 3 is a 4. So 4 times 12 gives me 48. So 48 ohms will become the best answer then. All right, then question number 2. A group of learners decide to design a device that contains that consists of a light ball on a string that is hanging from the roof of a cargo truck. The device is used to determine the acceleration of the truck when the truck is stationary or moving at a constant speed. The ball will hang straight down. But when it undergoes constant acceleration, the ball hangs down at an angle theta as shown. Okay. Then they want us to draw a free body diagram, okay, of all the forces that are acting on the ball. So if that's our ball, we know that there is a tension force, and then there's going to be weight there. So meaning that we're going to have something like that, and then we just drop it down. So that is weight, then that is your tension. All right, so that is what we would have written down. Okay, remember this is a component of the tension, which is okay, perfect. And then 2.2. In this case, the mass of the ball is 50 grams. So let's change this to kilograms. It's going to be 0.05 kilograms. Perfect. And then the angle theta is 18. Calculate the horizontal force on the ball. So one thing you need to remember is that if this is the tension that is acting, okay, if I'm to resolve this into the horizontal and the vertical, okay, gonna have something like that. So if this is a theta, even this one is gonna be a theta. I don't know how you want to do it, but this one is gonna be a t cos of theta. And then this horizontal of mine will be a t sine of theta, okay? But now, in which direction is it acting, okay? Is it to the left or to the right or what? So since this must be in balance, I'll take my horizontal to be in that sort of direction. Because remember, for me to get my resultant of T, one must be up, then one must be in this sort of direction, because I cannot put it to the right, otherwise this resultant will be in that direction. Okay, so then since they want the horizontal, I'll just do the substitution and say my T sine of theta is equivalent to the tension. Do we know the tension? Oh, this is a T cos of theta. I don't know. We can look for because the force is not going to come out without the T. It's 4 max. So if that's the case, then let me start by looking for because I need that force. Oh, what's the way forward? I can say that my T cos of theta is equal to mg. Okay, looking at just the upward forces. Then I look for T, which is going to be mg over cos of theta. So if I do that, then this is going to be my mg, which is 0.05 multiplied by 9.8 over the cos of 18. Okay, so what is my tension? So let's punch this, 0.05 multiplied by 9.8. You're dividing it by the cos of 18. That gives me a 0.52 newtons, okay? So that's our tension, meaning that for us to get the horizontal force, it's going to be 0.52 the sine of 18. Let's see. Sine of 18. That gives me 0.16 newtons, okay? So that is how I would have gone about with that question, okay? Remember, the rounding off just needs to be maintained to 2 decimal places. Okay, because my calculator was giving me something bigger than that, but it's okay. Then 2.2.2, they want the magnitude of the acceleration. Now, one thing we need to know, is there friction on this? Because it's consisting that determine the acceleration when the track is stationary or moving, okay? Okay, so the question never talked about anything to do with what? With friction, meaning that I can use my F net, okay, and say that my F net is equal to MA. So what is our net force? So we know that our net force is basically what we got as the horizontal, meaning that the 0.16 is equivalent to the mass, which is 0.05 A. Then divide both sides by 0.05, 0.05. Okay, when I punch that into my calculator, okay, 0.16 divided by 0.05, I'm getting a 3.2. This is meters per second squared. Okay, so that is how we calculate the acceleration of that body. Then 2.3, A and B are two identical blocks, each with a mass of 5 joined together by a light string. The blocks are being pulled together with a force of 65 at 40 degrees. The two blocks accelerate to the right using this acceleration, and then the tension is 26 in between. Okay, calculate the friction on each block. Calculate the friction on each block. Okay, so when you look at body A, if I try to sketch the free body diagram, okay, because I need to see how many forces are acting on A. So from A, we have the 26, okay? We say there is a frictional force, okay? And I think that's all. When I look at B, I'm going to look at the horizontal component, which is going to be like 65 cos of 40, okay? And then on the other side, I have the tension, which is a 26, and then I also have the frictional force. So I have more forces acting on this than on this. Okay, so come down and use the F net. Okay, we're saying F net is equal to MA, meaning that if we have, let's say, 26 minus our FK, we should be able to get the mass and then the acceleration. Mass is a 5, the acceleration is a 2.17. Okay, so I do the substitution there. Okay, meaning that my FK for A is going to be a 26 minus, what is 5 times 2.17? I'm getting 10.85. Okay, when I subtract from 26, I'm getting 15.15 newtons. When I look at the B part, I'll still use the same thing. F net is equal to MA, meaning that 65 cos of 45, we are subtracting 26, you're subtracting FK, it should give us the same mass and acceleration, which we got as 10.85. Okay, move this one that side, and then we transpose 65 cos of 45 minus 26 minus a 10.5 is equal to FK of B. Okay, let's not forget that. So it's saying 65 cos of 40, not 45. Okay, it's a cos of 40. Okay, we are subtracting 26, and then we are subtracting 10.85. This is 85. Okay, so the friction for B that I'm getting is a 12.94 newtons. Okay, so that is how we would have calculated the friction on each block. But then the question is asking, explain why the frictional forces are not the same. Okay? Why the friction forces are not the same. Now, one thing we need to know is that, yes, the blocks can be of the same weight, but they may not necessarily be made out of the same material. Okay? And then two, when you look at the angle, this 40 degrees, there is a way it's going to affect the friction that is acting on block B. And yet with block A, there's no angle, there's no force like that. that is acting on that. So to answer this question, we could say that we know that the coefficient is constant, okay, for a specific surface. So one, we can say that surfaces can differ. Surfaces can differ. And then the force, okay, the force on B is at an angle, meaning that it is only a single component, the horizontal component, and not the entire 65 that will work on it. Okay, it's at an angle which decreases the normal force. Okay, so that is what we would have done and said with that question 2. Question number 3, VPM. They're telling us that a ball is dropped from a height of 19.6 above the ground. It rebounds from the ground, reaching the original height h. Wow. Ignore the contact time of the ball with the ground and the effects of air resistance. And then they are asking us the definition of a projectile in physics. So we know that a projectile is basically an object, okay, an object which has been given an initial velocity, and then from the initial velocity it moves under the influence of the acceleration due to gravity, or we can say influence of the gravitational force. Okay, so that is the projectile one. We give it an initial push, an initial velocity, and then we let it go so that it moves under the influence of the gravitational force only. Okay, so that is a projectile. Remember, projectile could be different from free fall. Okay. Then 3.2, what is the total displacement of the ball? Remember, it was dropped from here. Okay, it covers 19.6 in that direction, but then it bounces back to the original position, meaning that it's a positive and a negative, which gives us a 0. Okay, then use equations of motion only to determine the time that is taken by the ball to rise up to the same height. Now, since we know that our displacement is a 0, we could use any equation that has displacement. Okay, question is asking for the time. So we have something like displacement is equal to V initial multiplied by time plus a half a t squared, or a delta t squared. Do you have the initial velocity? It is dropped, meaning that the initial velocity is a 0. Okay, I think we can use this. Can we use that? Yeah, we can use that. If not, we have V final. We don't have the V final, so we can't use the first one. And then the third one, V final squared is equal to V initial squared plus twice A together with the displacement. We don't have the final. So I think the second one will work best. Okay, let's see. Okay, so I'm gonna take the downward to be my positive. Okay, so meaning that start by writing the formula. Delta y is equal to V initial multiplied by delta t plus a half g delta t squared. Okay, so we're saying this is 19.6. Since the ball was just dropped, that's going to be 0 multiplied by delta t, which we are looking for, plus a half. The g is going to be 9,8 multiplied by t squared. Okay, this is a 19,6. A half of 4 or half of 9,8 is 4,9 t squared. Divide both sides by 4,9. Divide by 4,9. Okay. When I do that, what do we end up with? From my calculator, I'm having 19,6 divided by 4,9, which gives me a 4. And then take square roots, meaning that t is going to be 2. So if the ball took just 2 minutes to drop down, it should also take 2 minutes to go back to the original position. So time taken by the ball to rise up to the same height. So that is 4 seconds. Okay. And then 3.2, the velocity with which the ball leaves the ground after rebounding for 3 marks. So what we are basically looking at is that if we are ignoring the reaction time, then we shall assume that the velocity with which the ball leaves the ground is like the final velocity with which it hits the ground, if I'm to think of it critically. Okay, final velocity with which it hits is the same final velocity that it will use as the initial. So let me look for the final velocity using the first equation. V final is equal to V initial plus A delta T. So my A is going to change to a G, meaning that our V final is the 0. We say that is going to be 2 multiplied by 9,8 because the time is 2. Ish, someone will cry and say, but now you started with A, now you're putting a 2 first. Ish. So it's going to be 9,8 multiplied by 2. And then that gives me 19,6 meters per second. Okay, so that is what we're going to have, but the direction will be upwards. Okay, so that is how we would have claimed those 3 marks. Then 3.4, they want us to sketch a position time graph for the complete motion of the ball. Show the time taken for the ball to reach the ground, the time taken for the ball to reach the starting point, the initial and final positions. Okay, so one thing we need to remember about the position time graph. Okay, so this is the position which I'm going to just label as a Y. Okay, the displacement in meters. This is the time in seconds. Now it all depends on how you want to put your representation. Okay, so if I start from a 19,6, ball is gonna bounce. Okay, and then after the bouncing, it will go back to the same height. Okay, so now what's going to happen is that the point at which it reaches the ground is 2 seconds. And then this point here, the time needs to be 4 seconds. So I think that's all that I need to just represent, and then I'll get my 3 marks because we have all the factors that they wanted. All right, then question number 4, they're telling us that ABC, okay, ABC is a frictionless track. There is no friction. A is a point that is 6 meters above the ground. Blocks P and Q of mass 4 and 6 respectively. Okay, this is 4, that is 6. And the spring of negligible mass are clamped together so that if the fully compressed spring is aligned between blocks P and Q. Then at position A, the system moves as a whole, moves together, no stress. Okay, but they are moving at 4,5 meters per second. System slides down B at the bottom, and then boom, they break up. That want us to state the law of conservation of mechanical energy. in words. So we can say that the total mechanical energy, okay, total mechanical energy in an isolated system, is conserved or simply remains the same. Someone could also say that the sum of the gravitational potential and the kinetic energy in an isolated system remains the same or is conserved. Okay, so that is 4.1. Then 4.2, use the law of conservation mechanics to calculate the speed of the blocks at the bottom of the ramp. Now, one thing we need to know is at point A, okay, the blocks are having both the mechanical and then the potential because the blocks are moving. That's what they told us. Okay. That at position A, the system moves as a whole with that sort of velocity. But still at this position, there is also mechanical energy, the EP. So we have the EP and then we also have the EK. Now, at the bottom here, the combination is only having EK because the EP is a 0. Okay, we only have the EK, which will be the EK max. Okay, so what are we gonna do? I believe we just need to look for the mechanical energy and then try to work that out. I don't know if I can do it. It's fine, let me do it here. Okay, so let me start by finding the EP. Okay, the EP at A. That's gonna be mgh. So I'm gonna look at the combined mass, which is 4 and 6, which is a 10. So 10 times 9,8 multiplied by 6. What do we end up with? Okay, 10 times 9,8 times 6, which is 588. And then let's look at the EK at A. That's gonna be a half. Okay, I can look at the two masses because the velocity is the same. Okay, so a half of 4 multiplied by 4,5 squared plus a half of 6 multiplied by 4,5 squared, which would have been the same as me just adding up the two. Okay, so 0,5 multiplied by 4 multiplied by 4,5 squared. We are adding 0,5 multiplied by 6 multiplied by 4,5 squared, which gives me 101,25, meaning that my mechanical energy at A will be a combination of the two, which will be 689,25 joules. Now, I'm going to get this 689 and then I equate it to the EK at point B or along the flat surface. So I would say that we said 689. EK max is equal to a half mv final squared. So 89689. 25 is equal to a half multiplied by the entire system, okay, which is going to be a 10 multiplied by the v final squared. So that's going to be a 5. So 689,25. I'm dividing it by 5 and then finding the square root to get my v final. Okay, so punching that into the calculator, 689,25. We said we are dividing it by 5. We're getting 11,74 meters per second. So that is how we would have obtained those 4 marks, by just comparing the energies at the different points. Okay, that is how we would have answered 4.2. Then they're telling us that at the bottom of the ramp, the clamp is released by a remote control so that the motion of the system as a whole is not affected in any way. So as the spring expands or stretches, the blocks move apart. The speed of block A is now increased by 10%. Now remember, both blocks we're having the 11,74. Okay. Now, if it increases by 10%, what is it going to become? Okay, we're going to look at that. Use the law of conservation of linear momentum to calculate the velocity of block P after the spring has expanded. So what we're looking at is a scenario whereby we know that momentum before is equal to momentum after. Okay, so initially they were together. So it's a mass m of A, no, mass 1 and mass 2 multiplied by the final velocity is equal to mass of block 1, V fine of block 1, plus mass of 2 and the V fine of block 2. What did they tell us? That the speed of Q increases. So let me call this P and Q so that I don't confuse people. This is Q. Okay, so 10% of 11,74, what is it going to become? We know that that is going to be 0,1 multiplied by 11,74. Why don't I just say 1 at once? Because that's going to be 110 divided by 100 times 11,74, which becomes 12,91 meters per second. Okay, so that is the new velocity for Q, or the final velocity for Q. Then let's do the substitution. That's going to be 4 plus 6 multiplied by 11,74 is equal to the mass of P, which said it's a 4, multiplied by the final velocity of P, plus the mass of Q, which is a 6, multiplied by the 12,91. So let's transpose everything to that side and then see what we have. So 10 multiplied by that, I'm going to have 117,4. I'm subtracting 6 times 12,91, which becomes 77,46 is equal to 4 VFP. Divide both sides by 4, which means our final velocity for P is going to be 117,4. We are subtracting 77,46. We said we are dividing it by 4, which is 9,985. I'm tempted to round it off to 10, or someone can say it's 9,99 meters per second. Okay, so that is what we would have obtained, okay, as our answer. Then 4.4, they want us to calculate the magnitude of the impulse which block Q exerts on block P. Now remember, when we're talking about impulse, we're basically discussing the change in momentum. Okay, so impulse is equal to the change in momentum, meaning that our P final minus the P initial. This is given as M, V final minus V initial. So which M can we use? We can use the M of P, okay, which is basically the mass of P. And that mass is going to be 4. What is our V final? We said it's going to be 9,99. What is the V initial? We got it as 11,74. Okay, when you punch this into the calculator, it's going to be 4 into minus 11,74. It gives us a -7, okay? But remember, the negative simply indicates the direction that we're basically looking at. So meaning that our impulse is going to be 7 Newton per second. Is it Newton second or Newton per second? It's supposed to be a Newton second. Okay, so that is what we would have done in that particular aspect. All right, then we move on to the next part. Okay, then question number 5. Question number 5, they're telling us that a diver, okay, of mass 80 kgs steps off a diving board at point A, which is 4 meters above the level of the water of the swimming pool. Then the diver enters the water at point B and comes to rest at point C. While this guy is falling through the air, the average frictional force of 172 newtons acts on the diver, and then the total work done on the diver while he moves from A to C is that much. Then we have the picture. Okay, they want us to state the work energy theorem in words. So these are free marks, guys, whenever you see this question, because it's always there in almost all the papers. So we can say that the work done, okay, on an object, the work done on an object is equal to the change, is equal to the change in the object's kinetic energy. Object's kinetic energy. Okay, so that is how you have to put it. The work done on an object is equal to the change in its kinetic energy. Okay, then 5.2, use the work energy theorem to calculate the speed of the diver at point B. Okay, now what they gave us was basically the work done. Okay, so we can use that and say that W net is equal to the change in EK. Okay, now what we need to realize or understand is with the work that is being done, we have a frictional force, and then we also have this guy's weight. So before I even start, if I were to look at the free body diagram of this guy, okay, there's weight, and then we say there is a frictional force that is acting to oppose the direction of the motion. So since this guy is going down, meaning that the weight is going to be greater than the frictional force. So the work done by these two could be just the same as work done by the weight, which is the Fg, plus the work done by the frictional force should be equal to the Ek final minus the Ek initial. So work done, remember the formula is force delta X and then the cos of either 0 or 180. So the weight, this guy is 80, so it's going to be 80 multiplied by 9,8, because now that will be, because this guy is 80 kilograms. multiplied by 9,8 to get the weight. Okay. Then the cos of 0. Do I need to get the cos of 0 as well? Yeah, times 4 cos of 0 plus, they told us that the frictional force is 172 multiplied by the displacement, which is 4, and then that's going to be cos of 180 because it's opposite. Okay, if you want to avoid the cos of 0 and the cos of 180, just focus on the direction. So friction is negative, so then there will be no need of the 180 to come out automatically. So that is equal to the half mass, which is 80. We're looking for the velocity. Is that correct? Yes. So V final squared minus a half times 80, the initial velocity with which he jumps. Are we going to take it to be a 0? Definitely, because it's more like he's dropping himself into the pool. Okay, so when I look at the left-hand side, so 80 times 9,8 multiplied by 4, I'm getting 3136. Okay, now this is going to be minus because of the cos 180. 172 times 4 gives me 688. This should be equal to, this is a 0, which is 40 VF squared. Okay, so 3136 minus 688 gives me 24. 48 is equal to 40 VF squared. Divide by 40, divide by 40, meaning that our VF squared is equivalent to 2448 divided by 40, which is 61,2. Okay, and then let's find the square root on either sides. So our V final, 61,2 gives me 7,8 meters per second, 7,82. Okay, so the velocity with which this guy hits position B is 7,82 meters per second. Guys, so that is how I would have gone about that question. If you have a cheaper way or a quicker approach, please advise us. Then 5.3 is the mechanical energy of the diver conserved. Yes or no? Give a reason. Okay. Now, remember, we said under conservation of energy or mechanical what? We said in any isolated system, okay, the mechanical energy is conserved or remains constant, meaning that the net mechanical energy needs to be a 0. Okay, but when you look at this, they gave us the net to be, okay, the total work done is negative. So the answer is going to be a no. Okay, reason, the net work done is not 0. The net work done is not 0. Okay, someone could say that it's a no because there is presence of friction forces that will be doing work. Then 5.4, use energy principles only to calculate the distance from B up to C. Okay, so which energy principles are we going to look at? We can say that WNC, work done by the non-conservative forces, will be equivalent to the EK plus the EP. Okay. Then we were given our non-conservative, which is the -6, what. So the only thing that I need to look at is these changes. So I can have my EK final minus my EK initial my EP final, my EP initial, okay? When I do the substitutions, I have -6, 240. My EK final is going to be a half. The mass is 80. And then the velocity, remember this guy is going to be at the bottom because they told us this guy comes to a rest. Y falls through an average, okay, comes to rest at point C, meaning that our final velocity is going to be 0 there. We are subtracting a half times 80. The initial velocity is what we got, 7.82. Okay, 7.82, but squared. Plus the EP final at point C. Remember, C is more like, they told us point A, which is 4 meters above the level of the water. Diver enters, comes up, falls through air, and do we know the displacement there? Do we know the initial displacement? Because, okay, let's take the initial velocity when he was jumping. Does that make some bit of sense? If we say, okay, he was jumping, and then we want to look at that sort of whatever, meaning that we cannot use the 7.8 because the 7.8 is only representing the velocity at this point. And then at B, he has velocity initially and finally. So if I'm using just this point, or if I'm taking it from point B, because if I'm taking it from the initial position, then that will be a 0 even initially. It was supposed to be a 0. If I'm taking it from B, then this can be a 7.8 squared. Okay. Now, if I take it from B, my initial, my final is going to be the mass multiplied by the 9.8 and the displacement. So which displacement are we talking of? Is it going to be a D? Because there is looking at it from that perspective. And then there is also looking at it from a different angle. I don't know which one would make more sense. Okay, if I look at B as my point of reference, okay, if B is my point of reference, but it's not going to make sense initially and finally. It's fine. Let me just use the original reference grid to say that we're starting from point A, meaning that it's going to be a 0, and then that's going to be a 0. Then for the final, I'm going to have what are we going to have there? It's going to be -D because it's down below the pool. Then I'm adding the MGH, which is 80 times 9.8 multiplied by -4, which is also below. Okay, meaning that this dies out. Okay, and if that dies out, I'll have the -6,240 is equal to the negative. But why am I? Okay, let me simplify that. We know that 80 times 9.8 is going to give us negative 784. And then this is saying we're multiplying it by 4, which is 3136. Let's move it that side. It's going to be a plus 6240. 3136 gives me 3104 is equal to negative 784D. Divide both sides by 784. Okay, so when I divide that 784, I end up with a 395, which is like a 396. 396 meters. So that is how I would have worked that out. Okay. Then question number 6, which is the Doppler. They're telling us that an ice cream truck that is playing a tune approaches a stationary listener. Okay, approaches a stationary listener. In the street, the ice cream truck is moving at a velocity of 11 meters per second. Okay, and then the sound waves emitted have this wavelength. Then the speed of sound in air is that. Then they want us to state Doppler effect. Okay, so this tells us that the change, Doppler effect is the change in the frequency, some people call it pitch, of the observed sound. Why do we say sound? Let's call it observed frequency. Of the observed frequency by a listener, because of the sound source and the listener having different velocities. Because of the sound source and the listener having different velocities. Okay, so some people will also put it as the apparent change in the velocities. Okay, but then these velocities must be relative to the medium of propagation. So it's one long sort of a paragraph, but just try to remember. Okay. Then 6.2, they want us to get the frequency produced by the ice cream truck. Remember, they only gave us the wavelength. So we know that V is equal to F lambda. We need the frequency, meaning that it's V over lambda. The speed of sound in air is 340. You're dividing it by 0.34. Okay, you divide that, we're going to get 1,000 hertz. Okay, then now we move on to calculate the frequency as it's heard by the listener. We need the F frequency of the listener. Okay, so we can use the Doppler formula and see that frequency of the listener, start by writing the formula down, is given as V plus minus VL over V plus minus Vs times the frequency of the source. Now, what was the scenario all about? An ice cream truck approaches, okay? So when it approaches, meaning that the frequency heard is going to be greater. So it's V plus and then V minus times Fs. So let's substitute. What do they want? Or what are we looking for? We want the frequency of the listener. Okay, so it's going to be a 340 plus the velocity of the listener is a 0. And then 340, the track, we had 11 comma something, 11 meters per second. The frequency we got was 1,000. Okay, so that is what we would get. Then when we punch this into the calculator, so it's a 340 over 340 minus 11. We're multiplying it by 1,000. That gives me 1033. Okay, 1033.43 hertz. Okay, so meaning that the listener will get a bigger sort of frequency value compared to what was emitted. Then, how will the frequency that the listener hears compared to the frequency calculated in question 6.3 if the ice cream truck was moving away? Will it increase, decrease, or stay the same? So if it is the frequency of the listener, it's basically going to decrease. But if it was the frequency of the source, it was going to remain the same. All right, 6.5, state any other application of Doppler effect within our lives. Now we have very, very many, okay? Number one, we can use what we call the Doppler radar, the one that is mainly used by the traffic cops. Then we can also use it in the Doppler flow meter to measure the heartbeat of the fetus. Okay. We can also measure the speed of blood. Okay, you can say speed of blood in a Doppler flow meter. Remember, we said to measure the heartbeat of the fetus and so on and so forth. We have very many, but the question just wanted just one. Okay, consider the representation of the absorption spectrums of two similar stars. Okay, now what we are seeing is that there's a shift in the lines. It's like they are moving in that direction if you compare B and A. If you're starting from A, then they're moving that side away from B. So the question is star B moving towards A or away? So B is moving towards. Okay, so how do we tell that it is moving towards? Just look at the double line. Okay, we're going to use the double line as a reference. Okay, so what we can say is that the double line of B has moved to the red side. Or is it? No, it's blue side. Okay, we're saying the double line of B has moved to the blue side. Okay, once it moves to the blue side, meaning that it is moving towards the frequency or the wavelength is decreasing. Then what is this type of shift called? So this is what we call a blue shift when it's moving towards. Then 7.1, a small sphere. Okay, a small sphere A that is carrying a -5 microcoulombs hangs vertically from a ceiling by means of a string. Point P is 100 millimeters to the right. So let's change this to meters, which is going to be 0.1 meters. Did the charged sphere A lose or gain electrons to acquire this charge of -5? Now, we look at spheres to be neutral if they are not charged. Okay. Then the moment the net charge exceeds 0, then they've gained something. Okay. But now we're talking of electrons, and we know that electrons are negatively charged. So this sphere gained electrons. Okay. If it was a positive, then it would have lost electrons. For it to be more positive, okay, you lose electrons. And then 7.1.2, calculate the number of electrons lost or gained by charged sphere A to acquire this. Okay, so we use that formula of the N is equal to Q over E, whereby Q is the charge and then E is the electron charge. So you're going to have 5 times 10 to the -6 over, we can use the negative, there's no problem. The electron charge is -1,6 times 10 to the -19, okay? And then when you just punch this into your calculator, I'm getting 3,125 times 10 to the exponent of 13 electrons, okay? So that's how much was gained or was transferred. Then 7.1.3, they want us to calculate the electric field at P due to the charge. So formula for electric field is KQ over R squared. Okay, K is a 9 times 10 to the 9. Our charged sphere is 5 times 10 to the negative 6. You're dividing it by the distance, which we said was 0.1 squared. Okay, simplifying this, I'm getting 4.5 times 10 to the 6 Newton per Coulomb. Okay, so that is how we would have gone about with 7.1.3. 7.2. There is an identical sphere B that is carrying some charge that we know nothing about on an insulated stand. It's brought closer to sphere A. Then the charged sphere swings to the right. In other words, there's some bit of repulsion, okay? And then the angle created is a 30 with the vertical, and there's a tension of 25 newtons. Distance between the two will be 50 millimeters, which will be 0.05 meters. Okay, 7.2.1 is the charge on sphere B positive or negative? Repulsion happens just in the same signs. So this must be negative. Okay, so what is the reason? We know that like charges repel each other. Like charges will repel each other. All right, then 7.2.2, they want us to get the magnitude of B. Magnitude of B. Okay, so I think we can look at this thing if you try to do the resolving. Okay, whereby we look at the tension. If we are to resolve it, we're going to have the horizontal and the vertical. So my horizontal is going to be T sine, which is like 25 sine, okay? And then my vertical is going to be T cos of 30, and of which this T cos of 30 is also equal to the weight. But that is not a big deal because we already have what the T is. All we need is the force that is acting between these spheres, okay, which is a repulsive force, meaning that this force at B should be equivalent to the tension, the horizontal tension. I don't know, that's my understanding of this. So we're going to say that the horizontal component on this sphere A, because our focus is A, is going to be 25 sine of 30, which becomes 12.5 newtons. Okay. Then A is going to also experience a repulsive force in the opposite direction. Okay. Because there's repulsion everywhere. No, the sign is acting this side and then the repulsion is that side. Okay, so with the repulsion, I'll use the forces and say F is Q1, Q2 over R squared, the electrostatic force. So that's a 9 times 10 to the 9. Our Q1 was a 5 times 10 to the negative 6. This is B, which we don't know, should be divided by 0.05 squared. Okay. Then I'm going to equate this force because remember we say that this force is the same as the T sine of 30. So I will equate it to the 12.5. Do your magic, mean that it's going to be a 12.5 multiplied by 0.05 squared. I'm dividing it by the 9 times 10 to the 9 times 5 times 10 to the negative 6. Okay, so when you simplify this, I'm getting 6.94 times 10 to the negative 7 coulombs. All right, so that becomes question number 7, as expected, okay? We move on to the next question, which is question 8. They are telling us 3 identical light bulbs, A, B, C, each with a resistance of 8. Okay, so 8 ohms, even this one is 8 ohms. Okay, connected to a 12V with an unknown internal resistance as shown. The resistance of the connecting wires is going to be ignored. S is closed, and then the ammeter reading is 2. So where's the ammeter? So meaning that the total current is 2 amps. Then they're asking us to define the term electrical power. So electrical power is basically the rate at which work is done. Okay, rate at which work is done. Okay, then 8.2, calculate the reading of the voltmeter. Okay, so they want us to get the voltage that is across. How many marks is this? It's 5 marks, which is a lot. Meaning that we have the current, right? But we also have the values of the resistors. Now, A and B are in series, meaning that if we combine these two together, we have a 16 ohm. Now, this 16 and this 8, they are in parallel. Okay, so I'll say resistance A plus B becomes 16 ohms, and then the resistance between C and the overall result, the series, I'm going to say product over the sum, 16 times 8 over 16 plus 8. Okay, so I prefer to use this sort of formula because this is the resistance for the series. Now I'm looking for the resistance for the parallel. Okay, so we're saying 16 times 8 over 16 plus 8. I'm getting 5,33, which is the same as 16 over 3 ohms. Okay, now if this is the total resistance that we have, okay, that's the total resistance that we have. We have the ammeter. We were given the voltage to be 12. Is it the voltage or the EMF? It's the EMF. But then the switch was closed. Okay, so since we are looking for the voltmeter reading, we know that V is equal to IR. So it's going to be 16 over 3 multiplied by 2, which is basically 32 over 3. And when I punch that in the calculator, it's going to give me 10,67 volts. Okay, so this 10,67 is more like the external voltage. And then 8.2.2, they want us to calculate the internal resistance of the battery. So if I use the knowledge of external and internal, because this is the external voltage, I know that my EMF is given as V external plus V internal. Okay, so that's a 12, a 10,67, and then that's going to be the current multiplied by internal resistance. When we subtract that, okay, so what is 12 minus 10,67? That becomes 1,33, is equivalent to the current, which is 2R, and the resistance, so over 2 over 2. So what is our answer? I'm getting 0,67, meaning that the internal resistance is 0,67 ohms. Okay, so that is how we would have also worked out the internal resistance. If that is too hard for you, then you can even use the original formula for EMF, I into capital R plus R. We have the current, we have the EMF, we have the effective resistance, and then we're looking for the internal. I believe you can still get the same thing. Then 8.3. Can we compare the brightness of the bulbs A, B, and C? And let's justify our answers. Now, one thing you need to know is that the voltage across C is the same voltage, or is the total voltage across A and B. Okay, but A is having a different voltage. B is having a different voltage, meaning that our V, the 10,67, is the same as the voltage across C, which is the same as VA plus VB. Okay. Now, since these two are identical, they will split the voltage into two equal parts. Now, when you look at the current that is passing through the 8 is not going to be the same current that is passing through these two, because this is going to be 16. If it's 16, which means there's less current that is going to pass through the two bulbs, and then there's more current that is passing through C. Now, how do we answer this? So we can say that bulbs A and B are connected in series across the battery, meaning that they glow equally. Okay, so we're saying that A and B are in series. Let me put it this side. We're saying A and B are in series. Okay, and they also light equally. The brightness will be basically the same. Whereas C is in parallel with A and B. Okay, it's in parallel. Then the voltage drop across C has the same magnitude as the terminal potential difference. Okay, so since A and B split and C doesn't, okay, it's parallel to A and B. With C having more voltage than A and B, okay, we say the voltage is the same for both A and B, okay, but the total of A and B gives us C. Therefore, we're saying C will be brighter than A and B. So any explanation around that? Okay, we could use the current situation, the voltage, or anything. Then 8.4, they're telling us that the switch S is now opened. Okay, how would the voltmeter reading change? Choose increase, decrease. So the voltmeter will increase the reading. Okay, why? Because there is no current and the reading is going to be the 12, which is the EMF. What is the reason? The reason is that the external resistance has increased. Okay, external resistance has increased, and then the potential difference decreases. We're saying V internal decreases, and then looking at the equation of V external is equal to EMF minus V internal. Okay, we're saying that the terminal potential difference across the battery will increase. The terminal potential difference across the terminals will increase. Okay, so we're basically looking at what brings about the increase. So if the external resistance has increased, less current will be flowing, and EMF is a constant. Total current must decrease. Okay, anything around those lines would be perfect. Question number 9. We're almost there. They're telling us that the simplified diagrams below show two electrical machines. We have A, we have B. Then they want us to classify the above machines into a DC motor and generator. So number one, we have A, we have B. we need to classify and give reasons. So A is a generator. Okay. What is, because they said classify the above electron machines into a DC and give a reason in each case. So when you look at it, it's like this handle is for spinning, and then we get the electrical energy. So what we can say is that this generator converts mechanical to electrical. Okay, it converts mechanical energy to electrical energy. Now, when you look at B, it's like it's connected to a DC source. Okay, and if it's connected to a DC source, meaning that this is a DC motor. We had two options, either a DC motor or a generator. So this is a DC motor. And what is the reason? We say it converts electrical to mechanical. Okay, the 9.2, what type of generator is represented? So what type of generator is this? Now, with this generator, we are using the manual approach. So it's going to be a DC generator. Okay, but then the manual part is not the reason. The reason as to why it's a DC is because of the split ring. Okay, there is a split ring. A split ring, we call it a commutator. A split ring, or sometimes we have a split commutator. All right, then name the principle on which generators work. So which principle is that? Okay, so the principle that generators use is what we call the electromagnetic induction. Electromagnetic induction. All right, then which one of the following graphs RS represents the voltage output by the generator? Now our focus is on DC generator. Ne? So a DC generator, which sort of output is it going to have? So anything that is DC will always have these humps. Anything AC will have the sine graph. So graph S is the correct option there. The 9.5, if we have an AC generator that produces a maximum of this much, connected to a heater of 40 ohms, calculate the average power dissipated. So on our formula page, we have a formula as power average. Okay, so the average power just follows the same combination as power. So I can say V squared over R. Okay, but remember this average just works with RMS values. Okay, so meaning that I have to look for the VRMS if I have the Vmax. So come down and say that VRMS is going to be Vmax divided by the square root of 2, which is 311,13 divided by the square root of 2. Then we can do the substitution, okay? So 311,13 over root of 2, dividing it by the 40 ohms. So remember, resistance is always more like a constant. It never changes to maximum or RMS. It's just the current and the voltage. So when I punch this into the calculator, I'm getting 1210. 1210,00 watts. Okay, that is question number 9. Then question number 10, which is the last one. Study the table below, which shows the different colors, okay, of light and the frequencies they emit. So red has this frequency, yellow has that, green and blue, just like that. Define the term threshold frequency. So threshold is like minimum. Okay, so we're gonna say threshold frequency or minimum frequency. We're saying this is the minimum frequency of light that is needed to extract or to emit or to remove an electron from a metal surface. Okay, then a photon has this much of energy. Use calculations to determine what type of color. Okay, so for us to get the color, we need to find the frequency. So we can use the Planck's formula and say that this is 10.2 E is equal to HF. Okay, so if our energy is 3,72 times 10 to the negative 19 is equal to H, which is 6,63 times 10 to the negative 34 times the frequency. Let's divide both sides by the Planck's constant, 6,63 times 10 to the negative 34. That cancels that. When I divide there, my frequency becomes 5,61 times 10 to the 14 hertz. So the question is asking which color. Okay, so it's color green. Okay, color green is the emission that we are getting. Okay, then we move on to the next question. They are telling us that the metal, okay, metal casing has a work function of this much. So this work function is like the W naught. Which color of light will not release electrons from the surface of this metal? Okay. Now, if this is the work function, we need to determine the threshold frequency F naught, and then compare it with the frequencies that we already have. So come down and say that W naught is equal to H F naught. So 3,32 times 10 to the negative 19 is equal to 6,63 times 10 to the negative 34 times the minimum frequency. Do the needful and divide both sides by 6,63 times 10 to the negative 34. This cancels that. So our threshold is 5 times 10 to the negative 14. Now, if this is the minimum, anything that is above 5,0 is fine, is perfect. What is the question asking for? Which color of light will not release? Okay, anything below 5, so we have a 5, we have a 5,6, we have a 6. So meaning that red is not going to emit. So the answer here will be a red with our calculations. 10.4, explain what effect an increase in the intensity mentioned in 10.3 will have on the release of photoelectrons from the surface. Now, intensity in most cases has no effect, okay? Because what matters is the minimum frequency, the threshold. If you can meet the threshold, then we are good to go. Okay, so we can say that a change in the intensity will not have any effect, will not affect the frequency. So what effect? No change, no effect. Okay, then 10.5, calculate the maximum kinetic energy of the photoelectrons released from the surface when it is exposed to this frequency. Okay, so we need to use the formula for the energy. Okay, and then we know that E is equal to W naught plus EK max. Okay, our E is given as HF, and then W naught will be given as, I think it's the same question that we're looking at, the 3,2 times 10. Okay, so do I need to substitute now? No, let me substitute, it's fine. So the E, we said it's a 6,63 times 10 to the negative 34. And then the frequency we are having is 1,1 times 10 to the 15 is equivalent to the 3,32 times 10 to the negative 19. Question is asking, calculate the maximum kinetic energy. So plus EK max. Do your magic and then transpose everything to one side. So when it's supposed to be subtraction, not a division. Okay, when I multiply this and then subtract that, I'm getting 3,97 times 10 to the negative 19 joules. Okay, so that becomes the maximum kinetic energy. All right, guys, so that brings us to the end of this paper. I wish you guys all the best in your preparation. Be confident, believe in yourselves. It is possible. Then go ace that physics paper on Friday. Bye-bye for now. Let's meet when we're discussing the memorandum to the papers. Bye-bye.